Hello boys and girls. So in a video, I think 2 days ago, I talked about a particular kind of finite product, and in this video we're going to talk about infinite products. And first I want to motivate kind of my perspective a little bit, and then show you a formula that I have actually never seen anywhere in a book or anything like that. At one point I came up with that, and I was able to use it to, I don't know, answer some questions on math overflow and math stack exchange. So I think there's some merit to it, and I kind of share it in this video. Taking a step back, right here I have written down the series expansion of the exponential function as an example. My point here is that, you know, if we were to compute the value of e to the power of x, where x equals, let's say, 5, how would you go about that? Well, you need some algorithm that lets you compute the value, obviously. And one definition of the exponential function would be in terms of this infinite series. And if you want to do an actual computation, then this means if you use this formula, you have to end it at some point. So you would compute a series from n equals 0 to, if you do it by hand, I don't know, maybe 10. If I'm being generous here, if you're on a computer and you implement that formula, well, you can choose, I don't know, how many thousands. My point being, you break off this infinite series, but really the definition of the exponential function is the series if you take the limit of the upper bound to infinity. But also, you may know there is another definition of the exponential function, which in the limit in analysis can shown to be the same value. And this is this product here. And I say product because for every finite n, you know, the object is defined as the limit n to infinity, but for every finite n, let's say n equals 9001 in your precision, this would be a product of expressions 1 plus x, whatever x is, like x is equals 5, over 9001, and then you would compute what is its value, right? There would be, I don't know, 1.00 so and so. And then you would have to multiply this number together 9000 times. And if n is higher, then more often. So for any fixed n, let's say n is a big number, this is some product. Actually quite similar to what we had in the video today. But my point being, there's also the notion of an infinite product, even though the products that we are going to discuss in this video are not of this kind of form, because there's something special about this product, namely that in this formula the n is also in the body, here in the body of what is the product taken over, and this is the upper bound here, right? This is the same sense in which an integral is not an infinite sum in the simple sense that you would have like a fixed kind of expression that you have to sum up, but actually the thing that you take the product here depends on n, just in the same way that in the Riemann integral the expression that you sum over also depends actually in the upper bound and changes. In any case, there are some proper infinite sums. An example would be, for example, this expression here. So here it says, take the product k equals 1 to n and let n go to infinity of the expression 1 minus, let's say, 5 squared divided by k squared. And there is this nice formula here that says this product actually always equals this expression, the sine of pi times x divided by pi over x. But really, what does that say here? Well, for one, unless you use a simple value for x where you can kind of look up the value, usually if x is some generic real number, then you need another algorithm to just compute the sine, right? The sine for most people is also just a series expansion, and so you would have to do that. And really, pi is also not something that that is just given as a finite expression, like 2.5, but you also need an algorithm basically to go with pi to an arbitrary position. And so this is really a relation between a big product and a big sum. You can see it like that. On the other hand, then here is a kind of related expression, right? Here you have 1 plus 1 over 2k squared minus 1, and there's this nice formula, and I'm sure that if you were to plug in here an x, then there's maybe some closed formula which says, oh, this product is some other infinite sum. And then you might ask some more questions. So hey, what is actually that product? What is that product? What's that product? These two kind of questions are the questions that I answered on Math Overflow and Math Stack Exchange, because it's not like there are some kind of famous products that people are generally interested in. So this is kind of not textbook material. Maybe there's no good application found, so it's not treated as often. And so, but naturally, you can come up with this question, and you can try to find some upper bound and see, yeah, actually that converges against something. That will be, I don't know, something like 2.3 point whatever. But how would you actually approach this? And the problem is that if you compute a product like that, let's say you go to k equals, like from k equals 1 to 5, then you can by hand plug in the numbers, compute some expression, but then the answer of the limit n to infinity would still be, it's finite maybe, but it's still this expression that you already have times some other expression. So you cannot really separate this in the first place. You will say, oh, like if I go with k to 5, then it's, I don't know, let's say 2.17 times, and then another expression which is still an infinite sum. And so how can you kind of make a statement about the rest of, how can you separate these things? Like how can you split the this infinite product into a finite product and then some rest where the rest is not multiplied with your expression, because then you can kind of not judge as easily what the result would be. And for that matter, at one point I stumbled upon this insight. So basically you have actually this formula, and I'm also going to prove it because it's very simple really. It says that the infinite product over some sequence of numbers bk, where k is the index. If you compute this infinite product, and I start here at k, small k equals capital K, but you can also set capital K to 1, and that is actually the finite product up to an arbitrary number m minus 1, plus, and then the point being here that you have here plus, you have the product separated into a finite product and then some rest expression, and the rest expression is this expression here. So it's a sum from where you were left to m and then up to infinity, and then of bn minus 1, which will be a very small number, times again a final product up to the bound n here that you sum over. And I say bn minus 1 is a small number because if this product converges at all, right, then bk cannot be a big number. Because let's say all bk's are 2 or bigger, then this, you would multiply numbers together that are bigger than 2 with 2, 4, 8 and so on. So bk, if it's a very small number or goes against a small number, then it will go to 0, if you multiply 1/2, 1/4, and so if you multiply them together, you get against 0. If they are too big, then they go to infinity. So either it will be some complicated oscillating thing, in which case the question is slightly harder, but stuff that is converges to something, even though it's a final product, will be something like that. It will be 1 plus and then some expression that is generally small, like this here, right? Let's say 1 minus, let's say x equals 5, then you have 25 divided by 1, or 25 divided by, and then the next factor 25 divided by 4, 25 divided by 9, and so on, and then eventually, okay, I suppose that, yeah, 5 is not a good example because then this expression is 0. So let's say 5.5. But eventually you get to k equals some bigger number, and then this expression will get very small, and that's why the product even has a chance of being finite. Okay, and so this is actually an expression, and you can then say, well, you know, if I were to do the product over these expressions, let's say here this then s equals 3, right? To compute this or to give an estimate, you can say, okay, well, I go with m to 5, m equals 5, compute this expression to 5 products, I can do that by hand, and then I see, okay, and the rest will be a sum over where this expression starts with something like 1 over k to the 1 over 5 to the power of 3, something very tiny. So you can say, well, this product is basically this product, and the rest will, you can then you can do classical analysis and see, oh, this sum is, you know, is bounded by this number, and so you get some insight. Okay, and finally, to prove this expression, what we do is we say, okay, the product that interested us here, this product with an upper bound of, let's say, j and j to infinity, so this is the infinite product. So we look at a finite product and consider this again as sequence. So this is a sequence an, where each term in the sequence is determine the previous sequence times some new number, right? So this is just a definition of my a, and then this infinite product is really the limit of this sequence for n to infinity, right? Because if n goes to infinity, per definition, like if a is defined like that, then this holds here. And on the other hand, if you have any sequence and want to compute, you want to go to a higher number in the sequence, what you can do is this: you start at any point in the sequence, here at the point m, right? And then you go, you compute the sum over these differences from the point where you started to some other point. And this object here will naturally always just be the last point that you're at. So let's say I go from m to m plus 5, then it will be m, and then the sum will be, let's say m is 5, then a5, the sum over a6 minus a5, a7 minus a6, a8 minus a7, and so on. And you see, this term cancels with that term, and then that term cancels with the next one of this. So here you have this kind of cancellation, and what remains is really just the biggest number you end up here, right? I mean, I could play this with an explicit example, but I just want to take it with one slide today. My point being then that here you can then see that you can pull out an and just rewrite this as this expression. And if now, this an was just a general an, but if now this an is just a product, then this expression is also just the last term in the product here, right? Because here we go to n minus, this is a product of bk's to n minus 1, and all the bk's will be here, and here will be all the bk's times another one, and so this will just be one expression. So you see this reduces to that, and this is just a product that you defined here. So there you go. Of course, I mean, you know, I didn't do any epsilon delta gains here, so this works for the series where it works, obviously, just there. But I have good experience with my formula, let's say. Okay, so thanks for watching, subscribe, and see you if I'm motivated tomorrow.